Welcome this morning again to the grade 12s. I'm looking grade 12. Okay, let's just wait for a few minutes. We'll start at 22:06. This is your host for Maths is a Game. Hello, Labs. We are continuing on from the section that we started on inverse functions. We'll be continuing on with inverse functions. Okay. Morning. So to my grade 12s, I'm hoping to see you guys here. Grade 12s. Guys, we'll be going through inverse functions. Our second session of inverse functions. We started with inverse functions. We'll be continuing on with inverse functions today. So please join in, share the live if you need to. Okay, but let's gather here. And let's share the live to those that may need the live right now. We'll be doing inverse functions, part 2. For those who are joining in for the first time, you guys are more than welcome to go to my YouTube channel. It's grade 12, guys, grade 12. You are more than welcome to go to my YouTube channel. We have the link in the bio. You can locate the YouTube channel. It's called Maths is a Game. You guys can go on there and you can pick up the inverse functions as have been started there. So last time we looked at how to determine the equation of an inverse function. And today what we are going to do, we're going to look at how to draw a sketch of an inverse function. But before that, we are actually going to also look at something else as well that will help us in the journey of being able to sketch functions, okay? Especially with the grade 12 functions that we have, okay? So hope you guys can just hang tight, hang in there. We will start shortly. Just need to allow all the other people that would possibly benefit to join in. But can we like the live so far, and we can share the live with those that we think will need this section today. Okay, guess let's start. It's 22, guys. So all the others who want to join us will join us as we go along. So let's start. Okay, so we are looking at inverse functions. And specifically today, we'll be looking at the function and its inverse. All right. So last time we were together, okay, we looked at how to change a function to its inverse. Okay. And basically, if you look at this is a typical linear function. It's a straight line function. Now, if we were to convert this function to its inverse, what we do is we first write the function in terms of y and x. Remember, f of x simply means y. So we can write in the place of f of x, y. Then what we do is we swap the x and the y. In other words, we interchange, right? In the place of y, x, and in the place of x, y. Then we try and make y the subject of the formula. So x is equal to 2y minus 4 is the same thing as 2y minus 4 is equal to x. All I did is like I put this pen, the pen was like this, and all I did is I simply turned it around and I've placed it like this. Does that make sense? So basically what was this side now is simply just on the other side, if that makes any sense. Then I can make y the subject, so then I transpose the minus 4, I get plus 4, okay? Then I divide both sides by what? By 2, the coefficient of y. And that should leave me with y is equal to x plus 4 over 2. And then I can therefore say the inverse of the function of f is equal to x plus 4 over 2. Okay, hopefully you guys see and it makes sense to you and you understand what I've just done. Now, let's say I wanted to represent these two functions on a Cartesian plane. Let's say I wanted to sketch this function on a Cartesian plane. All right, so now here is the thing. All right, so f of x is equal to 2x minus 4. All right, in earlier grades, whenever you sketched a straight line function, we used to use what we know as the dual intercept method to basically help us sketch the function. So in other words, all right, what we would usually do is we would let x be equal to 0 in the function of f of x. So you can imagine y is equal to 2x minus 4. We simply let x be equal to 0. Okay, and then what does that do? It leaves us with y is equal to 0 minus 4, which is y is equal to negative 4. So the one point that we have when x is equal to 0, y is equal to negative 4. So that's one point that we can have on the Cartesian plane. Then after letting x be equal to 0, which is basically, this is what we refer to as the y-intercept, we let x be equal to 0. In order to determine the x-intercept, we let y be equal to 0. Now, basically, y-intercept simply means where the graph cuts the y-axis. X-intercept simply means where the graph cuts the x-axis. So we let y be equal to 0. So it becomes 0 is equal to 2x minus 4. Then we solve for x. Minus 4 we transpose to the other side. It becomes positive 4, of course. And then after that, what do? We divide both sides by the coefficient of x, which is 2. And then we get x is equal to 2. So that means the x-intercept, when x is equal to 2, y is equal to 0. So remember, when we write coordinates, we write the x value first, followed by the y value. We write the x value first, followed by the y value. So that's why you get 0 and minus 4, 2 and 0. Now if you go to your Cartesian plane, you go and locate 0 and negative 4. So you look for where y is negative 4. So we would have typically say this is -1, -2, -3, -4. So if you think about it quite precisely, this is where y is -4. At the same time, x is 0 is on the y-axis. Because like I said, this is the y-intercept where the graph cuts the y-axis. Because remember, this is the y-axis on our Cartesian plane. So 0 and -4 is this point. Then 2 and 0, all right, this is where the graph cuts the x-axis. 2 and 0. So on our number line, then we have 0, this is 1, this is 2, 3, 4, and so it goes. All right, so 2 and 0, where x is 2, it's here. And on the x-axis, this is also where y is equal to 0. So those are our 2 points for the graph. Okay, and all we can do then is we take our ruler and then we sketch a line, basically a straight line, because like I said, this is a linear function, so our straight line would basically go like that. So you would obviously use a ruler to do this, so that indeed your line is as straight as possible. Okay, right, so you guys will have to forgive me, because on my one hand I'm holding the phone and using a ruler will not be feasible. Okay, it's just one of those things, so hopefully you guys can understand that. Okay, but that's my function f of x. Okay, so we label that function. Okay, now what we can just do as well is we can just check when x is equal to 4 for this function. Okay, what is the corresponding y value? So if we were to substitute in this place, x is 4, we get 2 times 4, which is 8, and then 8 minus 4. So when x is equal to 4, the corresponding y value, if you substitute x is 4, 2 times 4 is 8, 8 minus 4 is 4, so that we get a corresponding value of 4. Okay, so we just, okay, so 1, 2, 3, 4. So you can see, guys, where x is 4, y is equal to 4. Okay, so that's basically there. So that's just another random point that I just want to see for the graph on that side, just so that I can have a very good grasp as to what's happening as well beyond the x-intercept. Okay, then let's go to the inverse of the function. Now listen to me and listen to me well. If you think about this practically, all right, if we are going to be drawing the inverse of this function, remember we've just found the points 2 and 0, 0 and -4, 4 and 4. So if you think about it practically, okay, whenever we are going to sketch the inverse of this particular function, remember what's the most significant thing that we seem to do every time we want to convert the equation or the function of a particular function to its inverse. There is something that we seem to do every single time, all right? And that is this idea of swapping our x and y. So I want us to think about this a little bit more. So if we are always swapping our x and y, this is what it simply means. Remember, for the function, we had 2 and 0. For the function, we also had 0 and -4. Our 0 and -4 were our y-intercept, whereas our 2 and 0 were our x-intercept. So if this is the coordinates for the function, and then, okay, so we obviously also looked for another point, 4 and 4, just so that we could have an idea as to what's happening, okay, further along. So what we can do is that for the inverse of the function, guys, we can take these coordinates that we had for the function, and all we simply do is we swap these around. So this, for the inverse, it will not be 2 and 0, but for the inverse it will be 0 and 2. what have we done? We made x become y, and then we made y become x. For the inverse, it would be simply negative 4 and 0. And then for the inverse, it would still be 4 and 4, because what are we doing? We are swapping, guys. We are doing the swap. Swap, swap, swap. So without even really going through the whole mindset of using the dual intercept method to sketch this, I can simply use the fact that I'm swapping my coordinates for the inverse of the function. So this was the original function, obviously these were the points, but then for the inverse, I simply swap around. And this is what's going to happen. So let's locate where is 0 and 2. 0 and 2 are basically y, where y is 0, where y, is 2 is here, okay, on the y-axis, but then where x is 0 is on the y-axis itself, okay, because along this y-axis, x is equal to 0 everywhere on the y-axis. So the point 0 and 2, there it is. Let's move on. Minus 4 and 0. What's minus 4 and 0? Where x is minus 4, where y is 0. So we go on our x-axis. So we have negative 1, negative 2, negative 3, negative 4. So where x is negative 4 is on the x-axis, where x is negative 4, because x is negative 4 everywhere on this vertical line. But then where is y 0? Y is 0 on the x-axis, so that's why we are on the x-axis. Then last but not least, we have 4 and 4. Where is 4 and 4? 4 and 4 is here. Okay. And guys, what we simply do is we draw a straight line. Okay, so you would use a ruler. I'm using freehand. You would draw a straight line like that. Okay. So hopefully you guys can see the straight line. Okay, can we see it, guys? So this would be what? This would be the inverse of the function. Okay, and all I did is I simply used the coordinates of the original function, and all I did is I just swapped the coordinates I had for the original function, because that's the essence of what comprises the inverse of the function. It's when we are able to swap those coordinates of the original so that we can get the inverse of the function. Now what you would then notice is that these two functions, okay, they are actually symmetrical along the line y is equal to x. All right, and that's very important to note. Okay, very, very important to note. Okay, so they are symmetrical. Inverse functions are symmetrical along the line y is equal to x. Okay, yeah, all right. So I don't know if there's any questions in the comment section, but if there are any questions, please. So I label the function here. This is the inverse of the function. I can clearly see the points -4, okay, which is -4 and 0. That is 0 and 2, okay, the y-intercept and the x-intercept. And then I have a point there where the two functions, they intersect. In other words, where they intersect each other. They intersect each other where x is equal to 4. And therefore, they are symmetrical along the line y is equal to x. Okay? Because inverse functions are always symmetrical along the line y is equal to x. In other words, we always say if they are symmetrical along the line y is equal to x, we also then say the following: they reflect along the line y is equal to x. So whenever you are asked to sketch a function where the function, a particular function, reflects along the line y is equal to x, all they are simply asking you to do is to sketch the inverse of that function. And that's very important to note. They are asking you to simply sketch the inverse of that function. So when they ask you to sketch a function that reflects along the line y is equal to x, what in essence they are asking you to do is to sketch the inverse of that function. So this is very important, okay, to note. I hope you guys understand this. The function, like I said, you have the original function, the fact that you can actually obviously write or convert the original function to its inverse, okay, as I showed you. Then you can actually use the dual intercept method to be able to what? To locate the points of that particular function. Once you have those points, okay, 0 and -4, 2 and 0, you can go then to your Cartesian plane, locate the points. This is 2 and 0. This is 0 and -4. Then we used an arbitrary point to actually locate another point and then sketch. Top of the morning, Bongozi. Then we used an arbitrary point, just took a 4, substituted in the place of x, checked what the corresponding y value is, we got 4. So then we have that point, we draw our straight line through those points, the y-intercept, the x-intercept, and another point. Then if we want the inverse, like I said, this is the points of the original function. This is the inverse function. So all we do is we swap around the points in order to have the specific points of the inverse function. So in the original function there was 2 and 0, but then the inverse is 0 and 2. So all we did is we swapped around. Original had 0 and -4, we swap around -4 and 0. Original had 4 and 4, we swap around 4 and 4. And then all we do is we locate those points. And what do we notice after sketching the two functions? That they are actually symmetrical along the line y is equal to x. Very important, that realization that all inverse functions are symmetrical, okay, to each other on the line y is equal to x. Therefore, there's a conclusion we can make that the inverse functions actually reflect along the line y is equal to x. So whenever they ask us in a very different way to sketch the inverse of a function, they may ask you to sketch the function that reflects along the line y is equal to x. You know then that they mean that they want you to sketch the what? The inverse function. Okay, so guys, that is the inverse function of a straight line function, and I just wanted to look at how we sketch that. So let's turn our attention now to another type of function which we refer to as the parabola function. Okay, so we are going to also do what? Okay, you want to look at how do we determine the domain. Okay, so let's just quickly look at that if you want to look at that for these two functions. So first and foremost, let's look at first the domain. Thank you for asking Jota Pagati. Jota Pagati wanted to see how do we then find the domain for each function. So for instance, this straight line function, f of x is equal to 2x minus 4. If there are no restrictions and it's a infinite function, as you see here, okay, there's no restriction. We are told that f of x is equal to 2x minus 4. Then we need to remember that for our original function f of x, the domain for a straight line function, maybe you guys can let me know in the comment section. Maybe you still remember, all right? If not, obviously I will help you out. Do we know what the domain of any straight line function is if it has no restriction? For instance, f of x is equal to 2x minus 4. We sketched this function. There it is here. Okay. If it's infinite in nature, what do we say is the domain? Okay. Do we still remember the definition of a domain? Domain simply means the possible x values where the function exists. So what are we saying basically? We are looking for which x values does this function actually exist? Where do we see the function existing? Does it exist everywhere for x? Or is there certain places where for x it does not exist? Okay, so if we look at a typical sketch of a function y is equal to 2x minus 4, which is this function, is there a place where this function, if you look, like I said, x values from left to right, because when we look at x values, we are looking from the left to the right. So on our number line, we are looking from the left to the right. Which x values does the function exist if we look from the left to the right? Okay, and let's just imagine that this number line extended beyond -4 all the way to positive infinity, and then it extended before -4 all the way to negative infinity. Is there a place for x where the function will not exist? Okay. Can we say something about that? Is there a place where the function will not exist? Okay, so Ujota Pagati says no. The function will basically exist everywhere. So I like what Pio has said in the comment section. Minus infinity to infinity. In other words, x is an element of real numbers. Okay, I love that. All right. So yes, if we look at the domain of this function, we can say two things. We can either say x is an element of negative infinity to positive infinity. So basically this is just to mean that the function exists everywhere for x. There's no place where the function will not exist if we are talking about a straight line function that is infinite in nature. So x is an element of negative infinity to positive infinity. We use open brackets because negative infinity and positive infinity are not finite numbers. They are actually just a concept that reveals to us that there is a never-ending nature in this function. It's continuous, it never ends, it goes on forever and ever in the positive direction and also in the negative direction. Or if we don't want to write our answer in that way, we can always say x is an element of real numbers. Guys, you can either write your answer this way, that's very much acceptable, that's your domain, or you can say x is an element of real numbers. It means the exact same thing as x is an element of minus infinity to positive infinity. So Pio, you are spot on. And Jota Pagati, thank you so much for your actually just the question itself to find out how do we write the domain. Now let's look at this very same function and look at how do we write the range. What is the range, guys? The range is simply the possible y values where the function exists. All right. So if you remember when I said the domain, we said there's a possible x values where the function exists. And when you look at the domain, you always look from left to right. Okay, from left to right. You check from left to right. And this arrow usually indicates that we go on forever in the left direction. This arrow also indicates we go on forever in the right direction. And you can see that there's no gaps in between as this function continues. So that means that for every x value, the function does exist. Hence we said x is an element of negative infinity to positive infinity. This is one way of writing the domain in interval notation, or we can say x is an element of real numbers. Okay. Now, if we look at the range, what is the range of f of x? The range is simply the possible y values where the function what? Exists. So in other words, this time we are looking from the bottom to the top. Okay? Look at my arrow's direction from the bottom to the top. So if we go to the function, the function itself, f of x, does the function exist everywhere for y? We are looking from the bottom to the top. So if you look at this function, the arrow here indicates that the function will continue. And then the arrow there indicates that the function will still continue. From the bottom to the top, where does the function exist? In other words, for y, does the function exist everywhere, or is there a place where the function actually simply does not exist? Okay. from the bottom to the top, okay, from the most negative y value to the most positive y value. Where does this straight line function exist? Where our y values are concerned, okay? Okay, so I'm gonna wait for you guys. What do you guys think? Does it exist everywhere? Are there places where the function does not exist? What do we say? Okay, so I'm hoping you guys can see that for y as well, there's no place where the function does not exist for y. So therefore, what can we say if we are writing the range of this function? Two things. We can say y is an element of negative infinity to what? To positive infinity. Okay, or if we don't want to write it that way, we can always say y is an element of what? Of real numbers. That is the range of f of x. Now, what about its inverse? Now, I want you guys, we will look at the inverse of the function so that we can make certain conclusions about the domain and its range. Okay, so first and foremost, this is the sketch of the inverse function for f of x. So this is the inverse, guys. This is the sketch as we had sketched it earlier on. So if we look at this function, okay, my first question, what is the domain of the function? Okay. Okay. So what is the domain of the function? Does the function exist everywhere? For x, meaning from left to right? Okay. I'm sure you guys can see that from left to right, the function does exist everywhere. So again, when we write the domain of the inverse function, we'll say x is an element of what? Of real numbers. If we look at the range as well, from the bottom to the top, this function, we know most of this function will continue endlessly as well. Does it exist everywhere for y? Yes, it does. From the bottom to the top, because this function will go on infinitely. So from the bottom to the top, without any gaps, because it's continuous, it means the function will exist for every real number for y. So that's why we say y is an element. We can either say from negative infinity to positive infinity, or we can say y is an element of real numbers. Okay, so guys, I'm gonna hold it right there because like I said, this is still the introductory phase of these functions. Okay, so the domain and the range basically is what we would have just looked at initially. We'll look at other things as far as interpretation is concerned, because I can see, for instance, Jotha is typing in the comment section about perpendicularity. We'll look at all those things as we approach the interpretation. Today I'm looking at sketching the function and its inverse, so we'll hold it right there for now. Okay, and then we can look at domain and range for now. So we have this function y is equal to x squared. Okay, so we want to look at now what type of function is this? This is a quadratic. Okay, so we came from looking at linear, now we are looking at quadratic. So how do we sketch this particular function? Okay, so first and foremost, let's determine its equation. So we know, okay, let's say it was f of x is equal to x squared. So let's determine its inverse. So what do we do first and foremost? The first thing we do, we write down obviously the original of the function. Then what do? We swap x and y. And then after swapping x and y, what do? We make y the subject of the formula. So therefore y squared is equal to x. We take the square root on both sides. Okay, and we write plus minus. Don't ever forget that, which means therefore y is equal to plus minus the square root of x. Okay, so seeing as though, guys, that this does not have a constant term, it means if we use the dual intercept method, we will only get one point, and that is 0, 0. So what we usually do then is, to make life easy for ourselves, all right, is whenever, guys, we don't have a constant in our parabola or straight line or our exponential function, let me advise us to say that we can choose 3 arbitrary points, and that is we can choose -1, 0, and 1 for our x. And then we can utilize these to basically get the corresponding y value so that we can get 3 distinct points that we can utilize to sketch the function. Let me repeat this one more time. Whenever you find that in your function you do not have a constant value, a constant term, so for instance here you have x squared, but its constant is 0, all right? So that means that if you use the dual intercept method, you are going to find that you get 1 point, and that is 0, 0. That will not be sufficient in this situation to be able to sketch the entire function. So what you do is you choose x is equal to -1, 0, and 1, so that you can actually see at least what is happening with that function, all right, for 3 points. So let's take this x value and let's go first and sketch the original function of f of x. So what are the corresponding y values if we substitute -1 in the place of x? Remember, when we substitute, guys, we substitute in brackets. So if we substitute -1, this is our x value, -1. We can even use our table function in our calculator, and maybe this would be probably a little bit more easier so that you can quickly sketch the function. All right, so what we do, if we want to use the calculator for the table method, we say mode, then we go and press 3. Okay, we press 3 because we want table, so we press 3 for table, and there we have it. You have f of x. Then you go and press alpha, because alpha allows you to choose all the red functions on your calculator. So what we want is x, so we go and press this button, and there you have it. You have x, and then you can place squared. Okay, you see, guys, f of x is equal to x squared, simply using our scientific calculator. Then we say equal. G of x would be a second function if we had one and we wanted to actually also show the tabular form of that function. When we press equal, where do we want to start? Remember, where we want to start at -1, because that's the lowest x value that we want. So we go and press -1, and then you say equal. Where do we want to end? We want to end at +1. So we go and press +1. And there we have +1, and we press equal again. And then our steps, it's right that from -1, the next number that we want is 0, and then from 0, the next number that we want is 1. So our steps, in other words, our difference, -1 plus 1 plus 1, so the step should be 1. That's fine. We press equal, and then there we have it. That's our table. When x is -1, the corresponding y value is what? Is 1. When x is 0, the corresponding y value f of x is 0. When x is 1, the corresponding y value is what? Is 1. So there's my table. It's populated without me having to do this one by one, substituting individual values. Okay, I can just simply use my calculator function so that I can be able to do what? To actually see these points. So please, guys, let's always do that whenever we are given a sketch and it has no constant term that is actually not 0. So these are our corresponding y values. Okay, your calculator has f of x. Remember, f of x does mean y. Okay, so that's still fine. So now let's go to a Cartesian plane. Draw Cartesian plane. Please, guys, whenever you draw yours, obviously you're going to be using a ruler and making sure that this is straight, that it's not like the way you see me. I am doing freehand because I'm using my other hand to hold the phone. Then what you do then is you have 0, 1, and -1. Corresponding y values. Okay, so we have -1 and 1. Maybe we can just put in 2 and -2 here so that we have a little bit more room. So 0, 0, where's 0, 0? At the origin. -1 and 1. When x is -1, which is here, corresponding y value is 1, which is here. So where do the two meet together? They meet here. So this is the point. Then last but not least, when x is 1, that's there. y is correspondingly also equal to 1. So where are we talking about? We are talking about this point. Okay, and then what we can then do is we can do the following. That is our parabola, in other words. I hope that makes sense. Okay, so that's our parabola. We have these points, 1 and 1, and then we have negative 1 and 1. That's our parabola function, guys. Okay, I hope that makes sense. Okay, and if you remember in grade 10, you guys referred to this as the mother graph. Y is equal to x squared. It was called the mother graph, the mother parabola graph. Okay, so we used the 3 points, negative 1, 0, and 1, got the corresponding y values, and then we sketched the original f of x function. So that is f of x. Now, I want us to then look at the fact that we sketched f of x, but we want to sketch at the same time the inverse of the function. Okay, and remember I used 3 points. So I had minus 1 and 1, I had 0 and 0, I had 1 and 1. All I simply do when I want to sketch the inverse, I swap. I take these very same points and I just swap them. So for the inverse, I will have 1 and negative 1. I swapped this around. Then I'll have 0 and 0. Swapped this around. Then I'll have 1 and 1. Swapped that around. So then the inverse of the function I want to sketch on the same set of axes so that you guys can see the inverse of the function sketched as well on there. So this is what we are going to do. We are just going to go to the same Cartesian plane, go and locate where 1 and negative 1 is. So when x is 1, y is negative 1. Where is that? Where x is 1, y is negative 1. So where x is 1, y is negative 1. So where x is 1, y is negative 1. So this is where we are talking, where x is 1, y is negative 1. This is the point. Okay? Then 0 and 0. Where's 0 and 0? 0 and 0 is still at the origin. And then last but not least, 1 and 1. Where x is 1, y is 1. Where are we talking about? We are talking about there. So this parabola is like this. Turns like that. Okay. Okay. Okay, so let's just say, yeah, so the point there and the point there. So guys, I'm sure you can see this. Okay, I'm sure you can see this. So this would be the inverse of this original function. Okay, and remember here, we have not placed any restrictions on the domain. All right, I know for those that have probably learned this already, they're like, okay, and then what's happening here? Say yes. So this is the original function f of x, and this is the inverse of the function. And what you should then notice is that still with these two functions, what is happening is that these two functions are both symmetrical with each other at the line y is equal to x. They are symmetrical with each other at the line y is equal to x. Okay, so this inverse function, the inverse of the function is this y is equal to plus minus the square root of x. Okay, so I just wanted us to see how we are able to sketch the inverse of a function just like that. Okay, so for now it's just us sketching the inverse of a particular function. Okay, now since we have done, okay, let's look at one more parabola type. Let's look at one more. Y is equal to negative 2x squared. All right. So this is free reign, guys. So just sketching the inverse. Y is equal to negative, let's say negative 3x squared. Okay. Ijotha phakathi, if you want to write the domain and the range, of course, domain of this function, this one, the original one, if you're looking at f of x, okay, where does the function exist from left to right? You can see, guys, that the function will exist everywhere. All right, so that means the domain of the function f will be x is an element of real numbers. Okay, if we are talking about the inverse of this the function itself. And then the range, the function obviously has limitations in the sense that it does not exist everywhere for y, the original function. It is actually limited to what? On the y-axis it exists, so from bottom to the top it exists on the x-axis and above the x-axis. So in other words, the range is going to be y is greater than or equal to 0. Okay, that is the function. What about its inverse? Okay, I'm sure you can see, guys, that the domain for the inverse of the function. Okay, so here basically what we can do is just simply do what? We can swap. Okay, so if the domain is x is an element of R, then what you can expect is that the range now will be y is an element of R. So x is an element of R, all you do is you swap the x and the y. So the domain, which was x is an element of R, now when you speak about the inverse, we say that the range is y is an element of R. We are swapping between the x and the y. What about the domain of the function? All we simply do is we swap, okay, with the range, okay, and basically we swap the x and the y. So the domain will be what? X is greater than or equal to 0. Okay, if we are looking at the inverse of this particular function. Okay, so it's a matter of just swapping around. Domain and range, you swap. Okay, so what was the domain of the function? All right, when you write the range, it's y is an element of that R. What was the range of the original function? When you write the domain, you simply swap the x and the y. Its x is greater than or equal to 0. Okay, so if we can hold that principle where domain and range is concerned, we'll be safe and well. Okay, I think what I want to do now, since my time is coming very close, I want to just sketch I want to do this because my time is, the time's pressing on, guys. It's pressing on. Okay, it's pressing on. I just want to do a sketch of a exponential function. Then I know that next time what I'll do is I'll do an integration of the two functions or the two functions together, and we'll look at interpretation. But for now, I just want to sketch the three functions so that you guys can see how do we sketch the original function, and then how do we see the inverse of that function. So let's look at this one. F of x is equal to 2 to the power x. So this is obviously exponential function. So first step, where before we even go and sketch the inverse of, the function itself, let's find what the equation of the inverse of the function is. So remember, guys, what do we do when we want to we want the inverse? We first write y is equal to 2 to the power x. Then what do? We swap. We swap first and foremost. We swap the x and the y. This becomes 2 to the power y. Then after that, what do? We write this in terms of log. So hopefully you guys still remember what we do whenever we write in terms of log. The exponent becomes the subject. Then 2 is the base. And then we write log x next door. Okay, very important. Okay, that you remember that. Okay, so very important. So this is then the inverse of the function. Log x base 2. Okay, so the original function is f of x equal to 2 to the power x. Then obviously the inverse of the function is expressed as a logarithmic function. Okay, we express it in logs, so it's log x base 2. Okay, now remember what I said, we want to sketch the function and its original. Now since this is an exponential function and the constant is 0, we are once again going to use our table. And in the table, we are going to choose the arbitrary x values -1, 0, and 1. Because this makes life very easy for us so that we can see the sketch of the function and how it comes about. So the arbitrary x values we choose is -1, 0, and 1. Then obviously we try and find the corresponding y values. And what better way to do that than to just use our calculator? It makes life easy. So you remember, guys, what did we say? We say mode, then we say 3 table, then you can punch in 2, and then you say shift, or 2, you punch in 2 first, and then obviously you go and use this particular button so that you can reveal the exponent part of it, and then you can say alpha, and then you can press the x so that you have 2 to the power x there. Then you say equal. Okay, now g of x. Okay, I suppose you can actually do the g of x, but remember, guys, to make life easy for ourselves, I mean, you could type in that inverse of the function, but to make life easy, we are just going to use the original function and then sketch. Where are we going to start? -1. We press equal. Where are we going to end? +1. Equal. The steps, it's right, it's 1. We press equal. And there it is. From our calculator, -1, the corresponding is 0.5, which is half. For 0, it's 1. For 1, it's 2. So there is our table. And all we do, guys, is we utilize this table to then sketch our f of x, the original function. F of x is equal to 2 to the power x. Now let's remember that this is an exponential function. Okay. Good morning, Yagbakal. So let's remember f of x is equal to 2 to the power x. This is an exponential function. And therefore an exponential function, remember, has a horizontal asymptote. That horizontal asymptote is based on the constant of that particular exponential function. So the constant that we have here that we do not see is 0. So the line y is equal to 0. In other words, our x-axis is where the function does not exist. It does not touch that part. So for instance, x is equal to -1. We can go then to our Cartesian plane, -1, 0, 1. Then corresponding y value, you have 1, we have 2, we have -1, we have -2. When x is -1, y is 0.5. So when x is -1, y is 0.5. 0.5 is between 0 and 1. So where do these points meet? They points meet right there. When x is 0, y is +1. That's there on the y-intercept. And then last but not least, when x is 1, y is +2. So when x is 1, y is +2. So for our exponential function, guys, we simply just sketch a nice, beautiful curve. Your function does not touch the x-axis. Why? Because that is its asymptote. Remember, y is equal to 0 is the function's asymptote. These are the points that we have. That is f of x. Okay. Then the inverse is simple. We don't have to punch this into our calculator, guys. Once we have the coordinates, of f of x, then it's easy to basically determine the coordinates of the inverse. So f of x, remember, we had -1 and 0.5 or half. We had 0 and 1. We had 1 and 2. So all we simply do when we come to the inverse, we swap these around. So let's go and swap. Let's play the swap game. We take this we swap it around. So 0.5 and -1 will be 1 point. Let's come here, swap this around. 1 and 0 will be the other point for our inverse function. Come here, swap this around. 2 and 1 will be the other points. So let's go to our Cartesian plane and locate these points so that we can sketch our inverse function, and it should be very easy from there. So we have the inverse point here, which is 0.5 and -1. When x is 0.5, so x is 0.5 right here, in between 0 and 1, like smack bang in the middle, and x is y is -1 here. So where the two meet, they meet here. Are we together? So that is this point. Then 1 and 0, where x is 1 and y is 0, we are right there. Then last but not least, where x is 2 and correspondingly y is 1. So where x is 2, y is 1, where these two meet is exactly here. Okay? And what you should then notice is that with your sketch, guys, with your sketch, this is the situation. And all I did was sketch the inverse using my points of the original. Didn't have to use the table. I just swapped around the points of the inverse, which I arbitrarily chose, and then I just go and sketch those points, as long as I know how to locate the points on my Cartesian plane. And what you should then notice is that once again, these functions, the function and its inverse, is symmetrical along the line y is equal to x. And these points, guys, you make sure that you have them and they are evident even to the person who's marking that, okay, this indeed is what? Is half and -1. This is indeed 1 and 0. This is indeed 2 and 1. You see? That needs to be very clear to the person who's marking your points. The fact that this is -1 and 0.5. The fact that this is 0 and 1. The fact that this is 1 and 2. And your function, your original must be marked. Your inverse must be marked. Okay? And it must be very neat, of course. Okay? Right, so with the swapping thing, once you have the coordinates of the original, guys, you just swap, man. You don't have to waste your time. Swap around the points and then you sketch your function. If we go to the domain and range, because I can sense that's coming up. Domain and range, let's look at the domain and the range of f of x, and then let's look at the domain and range of the inverse of the function. Okay? So if we look at the domain, this function, the original function, is there somewhere for x where the function does not exist? Does the function exist everywhere from left to right? Or is there a place where this original function, the exponential function, where it does not exist for x? Okay. Because remember, the domain is the possible x values where the function exists. So if you move from left to right, will the function be existing everywhere for x? That's the question. Okay? Because if you say yes, it does exist everywhere for x, then we can write the domain as being what? X is an element of real numbers. Or we can say x is an element of -infinity, open brackets, to +infinity. Okay? This is an indication that the function exists everywhere for x, the original function. What about its range? What is the range of this function? Okay. When we look at the range, we are looking at the possible y values where the function exists. And we look at that from the bottom up. From the bottom up. So does the function exist everywhere for y? I'm sure you guys can see that this original function does not exist below the x-axis, and it does not exist on the x-axis. So in other words, there is a limitation to where the function exists. The function exists only above the x-axis. So in other words, where y is greater than 0, that's where the function will exist, the exponential function. So we say y is greater than 0. We don't say equal, because remember, this line is the function's asymptote. The function does not exist where y is equal to 0. So we look at the function existing only above the x-axis. So we say y is greater than 0. That is the range of the function. Someone else in interval notation will say y is an element of, open brackets, from 0 to infinity, open brackets, from 0 to infinity. We don't say square brackets, we say open brackets, because 0 is not included, okay? It exists only above. So these are two ways in which you can write the range. You can either write it as y is greater than 0, y is an element of 0 to infinity. Here you can write it as x an element of r, or you can say x is an element of negative infinity to positive infinity. Guys, either way is right. You don't have to write both, you just write one way. Okay, so if you're sticking to interval notation, stick to it forever, so that you can consistently remember. Or if you're sticking to x an element of r, stick to that, consistently. Now, when we're writing the domain of the inverse of the function, guys, remember I said we just swap here. So the domain, all right, if the domain is x is an element of r, now here's the thing, guys, the range, okay, becomes the domain. And literally, it's like you are saying this here, x is greater than 0, but we swap. We swap, okay? And I can confirm this. So this here, all right, the range becomes the domain, but you swap the y and the x. So it becomes x is greater than 0. If you look at the sketch, it's exactly like that. This function, the inverse, this one, it only exists from the y-axis onwards. It does not exist on the y-axis, because this here is its vertical asymptote, the inverse of the function. It does not exist on this line, but it exists from this line, which is the line x is equal to 0, onwards. So that's why we say x is greater than 0. That's the domain. This function will exist only after the y-axis. So we say x is greater than 0. And you see what I said? I said we just swap around. The range becomes the domain. In other words, you just write this greater than 0, but then you swap the x and the y. So the domain of the function is derived from the range. Same thing here, this side. The range of the inverse function is derived from the domain. So we can say here y is an element of real numbers. And maybe you can ask yourself, how is that so? Is there a place for y where this function will not exist? This one. Okay, I'm sure you can see from the bottom, this arrow is going down and it will continue to go down infinitely. And this arrow is going on and on. So basically from the bottom up, there's no y value where this function will not exist. Hence we say y is an element of real numbers. So from the domain, we can derive the range of the inverse function, but we swap the x and y so that we can write down its range. Guys, that is it from me for today. So today, I hope you guys were able to grasp something. I will be taking this content and material, I will upload it on my YouTube channel very shortly. But thank you so much for joining in the session, guys. I hope it was fruitful for those that actually got something. I hope if the session was fruitful for you, you can comment in the comment section level 7. If the session was fruitful for you, comment in the comment section level 7, or you can just write the number 7. If it wasn't fruitful for you, you can just write the number 1. Okay, please guys, on my YouTube channel, you can just go to my bio. My YouTube link is there. I will be downloading this live session that I've done, and I'll upload it on my YouTube channel for those who want to actually watch and rewatch the session so that they can benefit a little bit more. China, you are very welcome. Very, very, I hope, you are welcome. You're very welcome. Very, very welcome. Let me love and leave you guys. I hope you guys enjoy your day. It's a Friday. I'm sure you guys are like, thank God it's Friday. Please have a good one, and I'll see you again. And remember, we're having these live sessions every morning at 5:30. Okay? And I think since tomorrow it's Saturday, yeah, we'll see how we can go about that. But yeah, 5:30 in the morning, we're good to go.